Alright, so hello everyone, welcome back to math. Today's recording might be a bit different. Okay, one thing I should say here first off, we only have 3 recordings left. There's 3 sections left. I'm going to do one a day, so we will have exactly 3 recordings left. Also, I had to record in a different area, so the sound quality might be a little different for these last 3 episodes. But hopefully everything should still go smoothly here. So, our topic for the day, for this video at least, I don't know why I always call it of the day, is convergence of formal homomorphisms. And throughout, we will be assuming K is a complete field with respect to a non-trivial absolute value. And we are, of course, going to be working in character 0. Brings us right away to our first theorem. If I can control this thing here. So, first theorem. So we're going to have 2 of these. We're going to have GI being G1 and G2, be an analytic group chunk, and Fi be the formal group law induced in K to the Ni by a chart Ci of Gi at its respective identity Ei. We're going to let taf from F1 to F2 be a formal group homomorphism. I might have to start writing a bit bigger because my screen is farther away. Then taf is convergent. That is, taf induces a local homomorphism of group chunks in taf hat from G1 to G2. And our proof, for both F1 and F2, Fi is convergent since it is obtained by passage to local coordinates from the convergent multiplication law on Gi. And since the conclusion of our theorem is local, we may assume, let's make that a period. We may assume that Gi is an open neighborhood of 0 in k to the ni. Sorry about that. With multiplication defined by fi. So first off, we have a special case where g1 is k, f1 is our traditional addition, g2 is g, and f2 is f. So in this case, saying that TAF is a formal group homomorphism is saying that TAF of S plus T is f of TAF of S and TAF of T, and that TAF of 0 is 0. Taking the formal derivative with respect to t, and then setting t to 0, we get that TAF prime of S is d2 of f at TAF of S and 0 times TAF prime of 0. That's supposed to be a 0, of course, not a 6. Since d2 of f of TAF 0, 0 is of course going to be d2 of f at 0, 0, which is going to just be the identity at in k to the n. This equation above is formally consistent, which is obviously a good thing. At s being 0. So now if we let phi of x be d2 of f of x comma 0 times TAF prime of 0 for TAF prime 0 being any fixed vector in k to the n. Then TAF prime converges from the following theorem. Alright. So in this case, we get our theorem. So, suppose that phi being phi 1 through phi n is a system of n convergent power series in n variables. Then the formal differential equation taf prime of s being phi of taf of s with taf of 0 being 0 has a unique convergent formal solution. And hopefully you've seen a proof of this before in something analogous to this in like an ODE or PDE course. Alright, then secondly we get the general case. Here we're going to let f be a convergent formal group law corresponding to a group chunk G. We're going to let X be in our algebra G, which is, of course, the algebra of our group chunk G. And then there is a unique map from Lx, L of X from K to G being a Lie algebra homomorphism such that it maps 1 in our base algebra onto our X chosen. By previous theorem, you have to lean forward whenever I need a new page. By previous theorem, there is a unique formal homomorphism phi x from K plus to F such that phi x prime at 0 is x, which is going to be convergent by our previous case. Now we're going to let each gi be L of our gi and a t be L of our taf. Of course, being a function from our first algebra to our second. Then phi x has the functorial property where phi of y is taf of phi of x formally for x being an element in G1 and y being t of x. Now, for setup, we're going to set n to be n1 and m to be n2, just to make things easier to write. I'm going to choose a basis x sub mu of G1, and we're going to let each y mu be T of X mu. We're going to define local morphisms k to the n. We have phi1 going to g1 and phi2 going to g2. By phi1 mapping a series t1 through tn to phi x1 t1 through phi phi xn of tn, and it's getting trackpad's getting really argumentative here all of a sudden. Phi2 of t1 through tn is phi y1 of t1 through phi yn of tn. The map L of phi1 from k to the n to g1 is the isomorphism of kn with g1 defined by sending the Muth standard basis vector of k to the n onto x to the mu, which makes phi1 is a tau at 0 and hence is a local isomorphism. Come on. In a neighborhood of 0. Now, formally, taf of phi1 is phi2. So formally, of course, taf is phi2 of phi1 inverse. So taf is convergent, since the right-hand side is convergent, we know already. Alright, brings us to a couple corollaries. First off, we have let G1 and G2 be analytic group chunks such that their algebras are isomorphic. Well then, first off, any isomorphism of LG1 with LG2 induces a local isomorphism of G1 and G2. Secondly, in the ultrametric case, well, let's see if I can just... So in an ultrametric, G1 and G2 have open subgroups which are isomorphic. And both of these are just immediate from what we have seen before. We also have a second corollary. Where G is an analytic group chunk, G is the algebra of G, and CH of G, come on, is the Campbell-Hausdorff group chunk associated to G. Then there exists a unique local isomorphism, which we can call the exponential, from CH of G to G, being a local isomorphism such that the Lie version, the algebra version of this exponential, is just the identity. Now let's some marks here. Suppose G is the general linearly group of some vector space V over K, of course. And we're going to let e to the x be our traditional x to the n over n factorial. We then contend that our exponential function above is just e to the x in a neighborhood of 0, in G being the endomorphisms of V. Well, we know by the construction of the Campbell-Hausdorff formula that e to the x defines a local isomorphism Sorry, one sec. This might sound weird for a second. I just want to double check something real quick. Sorry about that. Alright, everything should be good, hopefully. I'm thinking. So, by our local construction, EDX defines a formal homomorphism. A local isomorphism. EDX defines a formal homomorphism from the Campbell-Hausdorff group chunk of G to our base Lie group, and we have that L of e to the x is the identity. So exp to the x is e to the x by uniqueness. Now we're going to let k be our real or complex case, and G is going to be a Lie group over one of those. Since Fn of x is n of x in Campbell-Hausdorff group chunk of G, we can extend the exponential on G. Sorry. You can extend the exponential to all of G. So we're going to let x be in G. Then, since we're in the real or complex case, for n being a positive integer, one over n times our x is in the domain of the exponential. We're going to define the exponential of x just to be an exponential of this 1 over n times x to the n, which is obviously going to be independent of our choice of n. Now, for fixed x0 and some n, this formula is valid in a neighborhood of x0, which makes exp analytic. We also have that exp, our exponential here, is a tau at 0, but not necessarily a tau everywhere or bijective. Alright, we have 2 more corollaries we'll work through, and then we will call it here as a video. First off, suppose k is, once again, it's real or it is complex. Let G be a Lie group over k, and G be L of G. Then first off, we need G to be suppose that our Lie group is connected and its algebra is abelian. Then the group itself has to be abelian. Secondly, if the algebra in general is abelian, G, the group has to have an open abelian subgroup. And the first obviously gives you the second, so we just need to prove the first. First we note that since G is abelian, the Campbell-Hausdorff group chunk of G is G with the additive group structure. And we contend that the exponential defines a group homomorphism. So given x and y in G, choose a large n such that 1 over n times x, 1 over n times y, 1 over n times x plus y all lie in the domain where exp is a local homomorphism. Then the exponential of 1 over nx times the exponential of 1 over ny is the exponential of 1 over n times x plus y, which is the exponential of 1 over n times y times the exponential of 1 over n times x. So given this commutativity, by powers by nth power, by taking the nth power, we get that the exponential of x times the exponential of y is the exponential of x plus y, so that the exponential of g is an open abelian subgroup of G, and hence is G since G is connected. We've got one more corollary to show for this video here, this section, which I think is going to be a short one. Yeah, this is just an immediate corollary here that we can look at, then we're done. This is in the ultrametric case. So suppose K is ultrametric with a valuation ring of a let G be a Lie group over K of dimension n, such that our algebra, being the algebra of our group, is abelian. And then G has an open abelian subgroup isomorphic to our a to the n. And the proof is fairly quick. We're going to show here is just we have that the Campbell-Hausdorff group chunk of G is the additive group G. Oops. And it contains an open subgroup isomorphic to an open subgroup of G. And from that we can get our corollary pretty much immediately. And that's actually the end of this. So up next we have the third theorem of Lie, is what they call it. And then Cartan's theorems, which would be a fairly short one, and then we're at the end of our book. And after that I might just end the series for now after that, I guess. Because like I said, I need to catch up on some homework. Maybe in a month or so I will pick it up. But I feel like for now this is where we might be ending things pretty soon. So anyways, we'll see how that goes. Thanks for watching.